So, the first thing I want to talk about is turbulent shear layer. So, we are going to give up our governing equations completely, okay, and we are just going to look at how does actually turbulent flow look like, okay, if it is near a wall, and whether that information give us some lead towards solving flow in a pipe. That is stuff. So, what I have is a wall, a plain wall, okay, and there is a fluid that is flowing on top of it. I am not saying what is on the other side, I am assuming that the other side actually goes to infinity. If you look at the velocity profile, it is going to look something like that, okay, and it will go to wherever it wants to, where whatever the profile that is at far away or from at infinity. We are interested in a region where the velocity profile is affected by the plate. So, you can imagine that the fluid, when it is near the region very close to the plate, should experience that friction by the plate a lot, but when you if you go infinitely far from that plate, then the fluid should not see, whatever effect that you see should be independent of the plate. So, we are going to restrict to that region where the fluid is seeing the plate, okay, and I am going to give, let us say, some length which we do not know what it is, as some delta. Okay, so, delta is the length in which the fluid flow is really affected by the plate, okay, and I am going to now split this into 3 parts, okay, and that has been found useful. The first layer, I will just divide it and then talk about it. Okay. The first layer, okay, a layer very close to the wall, what do you think the turbulence stresses would be in that region? It would be almost negligible, because the viscous action will be very strong, okay, because the solid is giving a lot of friction to the fluid flow. So, that is the region where the viscous stresses will be much larger than the turbulent stresses, okay. So, this region is where tau, let us say, viscous is much larger than the tau turbulent stresses, and we call that layer wall layer or viscous layer. Okay. Now, this is really the outside fluid. So, let us call it a free stream. A free stream is basically that fluid which is not affected by the solid wall. The region between the free stream, okay, and a little bit inside, that is called outer turbulent layer. Okay, and in between you call something as overlap layer. So, why I am writing down it as 3 different layers is because the laws that govern the fluid. So, let me talk about this first. So, in the wall layer we found that tau viscous is much larger than tau turbulent. Okay. How about outer turbulent layer? It will be exactly the opposite. Tau turbulent will be much larger than tau viscous. So, in the outer turbulent layer you will have tau turbulent will be much larger than tau viscous. In overlap layer, tau turbulent will be similar to tau viscous. So, that is actually the difference between these 3 layers. Okay. We are saying that if you are looking at turbulent flow, we need to worry about viscous stresses and turbulent stresses. Very close to the wall, viscous action will be so strong, turbulent stresses will be small compared to viscous stresses. So, you have a wall layer, but if you go sufficiently far from the wall, then you will have turbulent stresses being large. So, turbulent stresses will be larger than the viscous stresses, and in between there may be a region where the viscous stresses and turbulent stresses will be of a similar nature. And why I am talking about these things is because now you know that in the governing equation, which actually contains the viscous stresses and turbulent stresses, depending upon which one is important or which one is more, you will get different solutions. So, in the wall layer, you are going to get some profile, in the outer turbulent layer you are going to get some other profile, in between you are going to get something else, and so on. Is that clear? Yeah. No, it will not be viscous free. It will definitely have viscous stresses as well as turbulent stresses. They are almost same. So, they are equally important. Both of them will be there. So, in other way of saying it is that, so that was the governing equation we ended up with, right. So, let me write the left hand side also. Right, that was the governing equation. If I am solving for the wall layer or viscous layer, in this equation, what all terms can I put to 0? If I am doing that, I can actually put this to 0, that to 0, and that to 0, and then try solving it, because I know that turbulent stresses will be small, and therefore you are going to get some profile, some velocity profile, right. Now, this must be undo. Okay. Now, if I am solving for the outer turbulent layer, okay, that is very close to the free stream, then I know that the turbulent stresses are much bigger. So, then I will put this, and that to 0, and that then I am going to get a different solution. Okay. In the overlap layer, I can't do either of them, I need to solve for the full equation. So, now you realize that you are going to get 3 different solutions. Okay. So, that is why we are actually dividing it into 3 different parts, and that is convenient, because we anyway do not know how to solve the full thing, that is why. Doubts? So, we are primarily going to depend upon experimental results and dimensional analysis. So, the first thing that we are going to analyze is the wall layer, and this was suggested by Prandtl in 1930. Okay. He said, let us try to write down some expression for the velocity profile, but we will just do a non-dimensional analysis. And he said the velocity profile is just going to be a function of how far it is from the wall. That makes sense, because it has to depend upon where it is. Okay. And instead of talking about how you are driving the flow, we will talk about a wall shear stress. So, you remember we talked about wall shear stress, we connected the wall shear stress to pressure drop and so on. So, instead of talking about what is driving the flow, we will really talk about what is the force that is acting on the wall. Okay, we will use that as the quantity, because that is a useful quantity to talk about, and that is what is really responsible for the flow. So, we will talk about that driving force in terms of tau W, and fluid properties like viscosity and density. I can't neglect viscosity, because we are talking about the viscous layer now, or the wall layer. Okay. So, this is what actually he experimentally found also. So, he says that there should therefore exist some relation connecting these quantities. So, if you write down some expression like this, now you know how to proceed, right. What is the next thing to do? We need to do the non-dimensional analysis. Can you do the non-dimensional analysis and find out what happens? What is the what are the two how many non-dimensional numbers would you expect? How many variables are there? 5. How many fundamental dimensions are there? So, how many non-dimensional numbers? Yeah, let us get them. Yeah. Ah.
The flow is turbulent, so there will be only turbulent phase stress only, no?
Yes.
No viscous.
Viscous stresses will be, so you are talking about free stream, right? Yeah, yeah.
Same as the third layer outer.
That's right. It will be very close to what's happening in the outer turbulent layer. So that we are keeping it free stream because that's a region where which is completely unaffected by walls. So for example, if it was a uniform flow that's coming, okay, we would say that free stream is basically uniform. It will not see the wall. But in the outer turbulent layer, you will still see the wall because that's a region where things are changing from the overlap to the completely uniform regime. So there will be some region where we could expect that the turbulent stresses are much larger, but still it is affected by the wall. Yeah. It is basically going to be the sum of both tau w. Okay. So it's basically the stress is basically the force that you need to apply to maintain the flow. Though in this, so by this analysis already tells you that when you talk about just tau w, we will be able to talk about only a viscous contribution to that, because tau turbulent will be much smaller there. So dimensions of u, L by T, y is length, tau w is newtons per meter square. So m L T square L square. So m viscosity is gram per centimeter second, m by L cubed. I just used Ibsen's method, you could do whichever you like. You could end up with some other combinations of these two quantities that I have written based on what method you have done. Yeah. Yes. Yeah, but you do not know what is the other quantity, right? Let's say the u prime, v prime. So, for example, what is the correlation between u prime and v prime? Okay. So, there is no real way to see that, though there might be this convention issue again, what is this stress? Okay. So, do you want to write your stresses minus mu dou u by dou y, in which case you would see that they are adding up. So, there must be something more to that. So, it is going to take away, so in terms of momentum transfer, okay, this is going to add up to your momentum transfer mechanism. So, if you think about how we interpreted viscosity, we said it is the fluctuating motion of the molecules that was resulting in viscosity. Now, we are saying that the fluid itself is fluctuating. Okay. So, therefore, in addition to viscous mechanism, there is this other mechanism that also will transfer momentum across. Okay. So, that is really the meaning of turbulent stresses. So, if you have wall and you are applying a force, that force is not only transferred because of the molecular motion, but also you could think about it as the fluid itself is basically fluctuating, and therefore, things get transferred much faster. Okay, and you will start seeing more and more uniform things than things having a gradient, and we will see that as an example. Okay, you got some form like that. I want to write this because that is going to be useful. Okay. Few more terms or definitions. Root of tau w by rho, okay, which is really a measure of shear stress on the wall, is known as friction velocity, and you typically represented it as u star. All right, and therefore, my relation is u by u star is equal to f of y rho u star by mu. So, if I replace root of tau w by rho, it is just u star, and u by u star is typically represented as a u plus, and this is represented as a function y plus, where y plus is y divided by what will be mu by rho u star. Okay, so, these are just, and therefore, u plus is equal to a function of y plus. It turns out that it is basically the right or the, so u plus and y plus are really non-dimensional numbers, okay, that you would want to use to represent the velocity profile in the wall layer. Just you could have written it in terms of the non-dimensional numbers that you have gotten. I am just following some textbook. I have not done anything, I have just written down u is proportional to some quantities and non-dimensionalized. And when I got a quantity called root of tau w by rho, I called it friction velocity. Is this actually, does it have the units of velocity? You could verify that, put stress divided by density and square root of it. Okay. Should I explain anything again? Should I go through again? Just going to say a few things. Okay. So, what have we been doing? Just let us revise. We started with looking at the governing equations. We wrote down a expression for the mean flow. We realized that the mean flow governing equations now not only contains viscous stresses, but it also contains turbulent stresses, and therefore, we need some sort of a constitutive relation for turbulent stresses, which we do not know. Okay, and therefore, we are leaving it at that point and then trying to do something simpler. And to do that, we started by looking at turbulent flow very near to the wall. okay, and then we are saying that, okay, look, I can take that region where the wall is affecting the turbulent flow, and I will be dividing it into 3 different regions depending upon what is the magnitude of viscous stresses versus the magnitude of turbulent stresses. That helps me to identify 3 regions, one region in which tau viscous is much larger, in the other region tau turbulent is much larger, and in between they are of comparable magnitude, and depending upon which one is more or less, you are going to get different solutions. Okay. So, now that is, so the first region we call wall layer, then there is an overlap layer, and then there is an outer turbulent layer. Okay. And then what I did is that, okay, now I will go with what Prandtl said in 1930, and he says that, look, the velocity profile in the wall layer can be written down as a function of few variables, which is distance from the wall, and the thing that is driving, which is tau w, and the fluid properties such as viscosity and density. And therefore, we wrote down that equation, and when we write down something like that, the first thing that we should do is to non-dimensionalize and reduce the number of variables. We found out what is the non-dimensional form of that function, and that came out to be just u plus is equal to f of y plus, where we do not know what is f at the moment, okay, and u plus and y plus are just 2 non-dimensional variables. And during this calculation, we also defined something called a friction velocity, which came out to be root of tau w by rho, which just happened to have the dimensions of velocity. It is no velocity at all, it is just a magnitude of tau w. That is all. That is all we have done. Okay. So, having done the wall layer, the next thing that we want to do is the outer turbulent layer. And for that, so all these calculations are essentially inspired by experiments, okay, or rather led by experiments, when you change things and see what is happening, and therefore, you try to write down the expressions. So, what Karman suggested is that, let us say in your free stream, okay, the outside the turbulent layer, the velocity is u, some u, which could be a function of space. He said, let us write down u minus u. So, that is the free stream velocity minus velocity in the turbulent layer as a function of course, distance from the wall shear stress which is driving it, but this time the viscosity is not going to come into the picture. You will still have density, okay, and he says this is also going to be a function of delta, which we defined originally, where delta referred to the total height of that entire layer. Okay. So, this is now if you ask me why he wrote down that, one can only say that it has been seen in experiments, and therefore, you are writing down. I do not have any more explanation to that. Okay. So, he suggested that these are the quantities that seem to be dependent on the u minus u, okay, the free stream velocity minus turbulent velocity is a function of few other things, and therefore, you could again non-dimensionalize and try to write down a non-dimensional expression for the outer turbulent layer. Can you do that? So, u is the velocity of the fluid that is outside this entire layer that we are considering, okay, and small u is the velocity in that layer. So, we are really finding out what is the difference of that layer compared to the outside layer. So, it is just that difference, and I do not think it would make any difference if you were to write it in terms of u, but it is convenient to, or this is the way he suggested so. And therefore, this is called a defect law. In fact, I mean, you know, basically it's how much is that difference. We will see that, yeah. Y we are taking. So, y is going to be the exact location. Okay, delta is going to be the total length. The total length that's affected by the wall. Okay, Now, so as I said, I have no answer why it should be a function, but this is what is seen, and therefore we are putting it into the expression. No, no, delta is the total height. So delta is the total height of the fluid layer that is affected by the wall. In fact, later you will learn that that's called a boundary layer thickness. While y is going to be the exact position. So you can expect that you should get something proportional to y by delta. Really like, radius of the pipe or whatever. So you will get something like this, just u by u star, u minus u by u star is a function of y by delta. Okay, y by delta is the only other parameter that's going to come. So this expression u plus is equal to is a function of y plus is called as wall law, and this is called a defect law or defect law. So this is the region where wall law is applicable. That's the region where we have the defect law applicable. Okay, and therefore this region which I am shading as blue should be a place where things change from this blue to the green. Okay, so the expression that should be applicable in the overlap layer should be an expression which smoothly changes from the wall law to the defect law. Okay, so that's the way it was interpreted, and therefore people were actually able to derive an expression for overlap layer, some expression that will match with these two regimes. Okay, so I am talking about something in between, where if I say that if my y is very small, then it should be like my wall layer. If my y is very large, it should be my defect layer. So what could be something in between? Okay, we don't derive it, we are just gonna take the result and proceed. I'll write down. So this was actually done in 1937 by Millikan, and he said if you write u by u star is equal to 1 over k ln y u star divided by nu plus b, this is the so called overlap law. This overlap law will smoothly merge into the wall law and the defect law. Okay. Now, what is new? Okay, mu by rho. This is also called a logarithmic law, and therefore sometimes this is referred as logarithmic overlap layer. This is a log function connecting the velocity with distance. It's found out that experimentally k is approximately equal to 0.41, b is approximately equal to 5.0. So in some sense what we have done is we just looked at a turbulent shear layer and we wrote down 3 different expressions, each applicable in a layer. Okay, and we will try to see how these expressions can be utilized further to analyze turbulent flow in a pipe, and we will see that in the next class.